In this lecture, we're going to talk about polyprotic acids. So a polyprotic acid is going to have multiple acidic hydrogens. So it's going to ionize in steps. So looking at this sulfuric acid, we have two acidic hydrogens. Got one here and one here on this oxo acid. So this is a diprotic acid. And so the way this will react in acid-base reactions is first you'll lose one of your hydrogens and then the second one. And so there's actually two separate equilibrium constants for completely ionizing sulfuric acid. So you have, you start with H2SO4, which is a strong acid, plus water will give you HSO4 minus plus H3O plus. So this is Ka1, our first Ka. Now this is a strong acid. And so we're going to form products almost entirely. Then in the second step, we have our HSO4 minus that'll react with water. And it will form SO4 2 minus plus more H3O plus. And this is Ka2. And Ka2 is going to be smaller than Ka1, as we show here. And this is because we already have a charged ion when we have HSO4. And so forming a -2 charge, something that has a larger magnitude, will be less favorable. And so we just see a smaller equilibrium constant for this reaction. Generally, with polyprotic acids, that first Ka value is so much larger than the other ones that the second or third ionization doesn't contribute very much to the overall H3O plus concentration. And so one exception is sulfuric acid, and it's good to know how to handle these problems anyway. And so we'll do an example of sulfuric acid, and then we'll do a practice problem in our later practice problems of phosphoric acid. Oh, so here first are a few examples of Kas for different polyprotic acids. So as we just talked about with sulfuric acid, our first Ka is strong, so it's large enough that we can assume it all ionizes. And our second Ka is 1.2 times 10 to the -2, which is actually a large Ka for a small Ka, for a weak acid. Looking at oxalic acid, our first Ka is on the order of 10 to the -2, and then the following one is 10 to the -5. And then sulfurous acid, 10 to the -2 for our first Ka, then 10 to the -8. So this second ionization on sulfurous acid happens at a very, very low concentration, and so it won't impact your overall pH. For phosphoric acid, we have a 10 to the -3, then a 10 to -8, and then a 10 to the -13. So for all of these, you can typically approximate them just with the first K, an ionization of your polyprotic acid. But let's walk through one of these because it's also an interesting exercise in an ice table problem solving. So here is sulfuric acid's two ionizations. We start with sulfuric acid and form HSO4 minus, which becomes the starting material for our second ionization, and it'll form sulfate. So we're going to assume, since sulfuric acid is a strong acid, that all of it ionizes and turns into HSO4 initially. We know that our Ka is 1.2 times 10 to the -2, and our question is asking, what is that concentration of H3O plus at equilibrium? And we're going to start with a 1.5 molar solution of our sulfuric acid. So I'm going to walk through and solve this problem on another page here. Okay, so I have the second ionization of sulfuric acid written out as a chemical reaction, and the information that was given to us in the problem, that we have 1.5 molar sulfuric acid and that we have a Ka2 of 1.2 times 10 to the -2. So because sulfuric acid is a strong acid, that means that concentration of H2SO4 will equal the initial concentration of HSO4 minus. All of it will ionize. And so that means our initial concentration for our HSO4 minus in our ice table is 1.5 molar. So now thinking about this reaction, our H2SO4, when it reacts with water, is going to form not only HSO4 minus, but also H3O plus. So that means that our H3O plus concentration initially in the second reaction is also 1.5 molar. Now remember, we're going to ignore water because it's a liquid and it's not going to play a role in our equilibrium expression, which for our second reaction here is going to be equal to the HSO4 minus times, sulfuric acid, sulfate. Sulfuric acid, hydrogen sulfate, and sulfate, they all sound so similar. So SO42 minus and H3O plus are our products, and HSO4 minus is our reactant for Ka2. And so our initial amount of sulfate that we have is 0. Now this is one of those situations where we have non-zero numbers on both our product and reactant side. So at this point, we could calculate a Q and compare it to our Ka2. If we did that, we would calculate that we would have 0 times 1.5 divided by 1.5. And so we would actually get 0 for our Q, which is going to be less than our Ka2. So we're going to proceed towards products. Also, anytime I see a 0 in my initial concentrations, I know that I'm going to have to form some of that either reactant or product to reach equilibrium. So that means my change is going to be minus X from my reactant side and plus X from my product side. And my equilibrium concentrations will look like 1.5 minus X, X, and 1.5 plus X. So I'm going to plug these into my Ka2 expression right here. So my Ka is equal to 1.2 times 10 to the negative 2. And I'll have X for my SO4 2 minus, 1.5 plus X for my H3O plus, and 1.5 minus X for my HSO4 minus. So now to solve for this, I am going to multiply both sides by 1.5 minus X. And when I do that, I'm going to get 0.018 minus 0.012X. Sorry, I'm switching from scientific notation to regular. And that'll be equal to 1.5X when I distribute this X out, plus X squared. So I'm going to need to use a quadratic equation to solve this. And so I'm going to subtract X squared and subtract 1.5 minus X from both sides. And I'm going to get an expression that looks like 0.018 minus 1.512X minus X squared will equal 0. So if I plug this into my quadratic expression, I'm going to get solutions for X equal to negative 1.524, which doesn't make any sense, or 0.012, which does make sense. So that's my value of X. So at equilibrium, my concentration of H3O plus is equal to 1.5 plus 0.012. So that'll be equal to 1.512 molar. If I take the pH of that, I'm going to get a pH of, if I take the negative log, it's going to be small, negative 0.179. So less than 0. So when we approach these polyprotic concentration of hydronium ion or pH questions, The thorough way to handle it is to walk through and do subsequent or like cascading ice tables, where you can solve for an equilibrium concentration or for the initial concentrations to your problem. And then if this was a triprotic acid, we would take these equilibrium concentrations and they would become the new initial concentrations of the third ionization. So we'll try on your own, and then I'll post a solution of phosphoric acid going through all three of these ice tables, one right after another.